Ever stop to think about how we actually tell computers what to do?
Hmm.
I mean, everything from a simple tap on your phone screen to, really complex calculations, it all comes down to instructions.
It really does.
Now, imagine trying to speak directly to the machine using only, well, ones and zeros, binary. That sounds tough.
Yeah. Incredibly difficult. And that's exactly where programming languages step in. They act as a kind of bridge.
Okay. And today we're taking a deep dive into one specific language, Python. It has this reputation for making that instruction-giving process surprisingly approachable.
Exactly. You can think of Python almost like a translator. Instead of that really complex binary code, we get to use words and symbols that are much closer to, well, human language.
Right. Things we can actually read and understand.
Precisely. Python takes those instructions we write and then translates them, converts them into the zeros and ones that the computer's core, its CPU, can actually process.
Okay, so fundamentally, programming is all about creating these step-by-step guides, these instructions, for a computer to follow and get tasks done.
That's a great way to put it, like a very, very detailed recipe.
And there are tons of programming languages out there, but our focus today is really on the basics of Python.
Yep.
We've got some really interesting learning material here that covers quite a range, from Python's role in cybersecurity, which sounds fascinating,
Mm-hmm.
to the absolute fundamental building blocks you need to write any code. So our mission, if you like, is to pull out the most crucial information to help you get started with Python.
Sounds good. And that recipe analogy is apt because, the computer follows it precisely. The CPU, the brain, it only understands binary.
Yeah.
So every single line of Python we write, it has to be converted in the end.
And Python, you're saying, makes that conversion process easier for us humans.
Definitely. Its syntax, the rules of how you write it is less complex, more intuitive than many others, and certainly miles away from binary.
Okay. And it's not just for one specific thing, right? Our sources mention it's used for all sorts of tasks.
That's right. It's what we call a general purpose language. So yeah, you can build websites with it, analyze huge amounts of data, automate tasks.
Which brings us back to that cybersecurity point.
Exactly. And when we write Python code, there's this program called an interpreter.
Ah, the interpreter.
Yeah, it reads our Python code, usually line by line, and translates it into instructions the computer can execute right away.
Now, something the learning material pointed out is that there are different versions of Python. It mentions Python 3, which is what the sources focus on. Why does the version matter? Is it a big deal?
It can be a very big deal, actually. It's a key practical point. Like any language, programming languages evolve over time.
Sure. New features get added.
Right. And sometimes the basic rules, the syntax, can change, even if just slightly. So if you try to run code written for, say, an older version like Python 2 using a Python 3 interpreter,
You might get error.
you'll likely get errors, yeah. Because the interpreter doesn't understand the old syntax in quite the same way.
Mhm.
So knowing which version you're using or which version the code was written for is pretty crucial for compatibility. It ensures your code actually runs.
Okay, that makes sense. So Python user-friendly, versatile, but be mindful of the version. Let's zoom in a bit on that cybersecurity application you mentioned. How is Python making a difference there?
Oh, it's become a really vital tool for cybersecurity pros,
No.
largely because it's just so good at automating tasks that are, well, repetitive but absolutely essential.
Like what kind of tasks?
Well, think about the sheer volume of data security teams deal with. Just mountains of logs, potential malware samples coming in, constant network activity.
Right, trying to find the needle in the haystack manually sounds impossible.
Pretty much, or at least incredibly slow and, prone to human error. So this is where Python shines. You can write scripts to automatically sift through logs looking for suspicious patterns, or to analyze malware samples to figure out what they do. Managing access control lists, who gets access to what, detecting intrusions, checking if systems are compliant with security rules, even scanning networks for vulnerabilities.
Wow, okay. So it handles the grunt work, freeing up the human experts.
That's a big part of it, yeah. It allows security teams to shift from just reacting to alerts to more proactively hunting for threats, doing the more complex analysis.
That sounds incredibly valuable. Okay, so if someone wants to start writing this Python code, where do they actually do it? The sources talk about different environments.
Right. There are a few main places you can work with Python. The learning material we're looking at puts quite a bit of focus on notebooks.
Notebooks, like Jupyter Notebook or Google Colab.
Exactly those kinds. Think of them as interactive web pages, basically. You can write your Python code, run it, see the output, and also write explanations and documentation, all in the same place, right in your browser.
Okay, that sounds really convenient, especially for learning.
It really is. They're structured with cells. You have code cells where you type and run your Python code.
You just hit a run button or something.
Yeah, usually a little play icon, and the output pops up right below the cell. And then you have markdown cells.
Markdown. That's for formatting text, right?
Yeah.
Like headings and lists.
Exactly. It's a simple way to format text, to describe your code, explain your thinking, structure your analysis. Really good for documenting as you go.
So notebooks, mix code, and explanation. What are the other environments? IDEs were mentioned.
Right, IDEs, integrated development environments. These are more like full-blown software applications designed specifically for writing code.
More features, maybe?
Generally, yes. They often have things like code completion, suggestions, tools to help you spot errors, maybe even automatically fix some.
Okay.
And features for managing larger projects with multiple files. They usually have a graphical interface with lots of panels and options.
And the third one was the command line. That sounds a bit more old school.
It is, in a way. The command line is a purely text-based interface. You type commands to tell the computer what to do.
Like navigating files.
Yep, you can navigate files and folders, but crucially, you can also run Python programs directly from there. It's a very direct way to execute scripts, often used for automation and system tasks.
Okay, so notebooks for interactive learning and mixing code with text, IDEs for more complex development with extra tools, and the command line for direct execution. Got it. Now let's get down to the real nuts and bolts, data types. What exactly is a data type in Python?
Think of it as a category. It tells Python what kind of information it's working with. Is it text? Is it a whole number? A number with a decimal? Is it just true or false?
And why does Python need to know the type?
Because the type determines what you can do with the data. You can do math with numbers, but you can't, say, mathematically divide a piece of text. Knowing the type prevents errors and defines the allowed operations.
Makes sense. So what are the core types our material covers? Let's start with strings.
Okay, strings. Strings are basically sequences of characters. That can be letters, numbers, symbols, spaces, pretty much anything you can type.
Like text.
Exactly, text. The key thing in Python is that strings are always enclosed in quotation marks. The course material uses double quotes, like updates needed or even 20%. An empty string, just POUD, is also valid.
And you can display them using that print function.
Yep, print is your go-to for showing output, including strings.
Okay, so strings for text. What if you need a collection of items, like a shopping list or a list of users?
Then you'd likely use a list. Lists are ordered collections of items, and those items can be, well, pretty much anything: numbers, strings, even other lists.
How do you write a list?
You use square brackets, and you separate the items inside with commas, so like 12, 36, 54, A, B. An empty list is just
And you can print lists, too.
You certainly can. Another important thing about lists is that they are mutable.
Mutable, meaning changeable.
Exactly. You can change the contents of a list after you've created it,
Yeah.
add items, remove items, change items. They're flexible.
Okay, strings for text, lists for ordered, changeable collections. Now numbers, integers and floats.
Right. Integers are whole numbers, no decimal point. They can be positive, negative, or zero. So negative 100, 0, 500. Just the number itself, no quotes.
And you can do math with them, obviously.
Yep, standard math. 5 plus 2 gives you 7. Floats, on the other hand, are numbers with a decimal point, like negative 2.2, 0.0, 1.34. Again, no quotes.
And you can do calculations with floats, too. 1.2 plus 2.8.
Gives you 4.0, exactly. You can do math with both.
Now, the material mentions something specific about division, how it works differently sometimes, with and Brune.
Yes, that's a good point to clarify. The single slash is standard division, and importantly, it always results in a float, even if you divide two integers that go in evenly. Like 10.2 gives you 5.0, not just 5.
Okay, always a float result. What about the double slash one?
That's called floor division, or sometimes integer division. It divides the numbers, but then it basically throws away the remainder, rounds down to the nearest whole number.
So 10.3 would be?
Just 3. It discards the 0.333 part, or 1.4 would be 0. If you use floor division with floats, like 7.0 to 2.0, you still get a float, but it's the whole number part rounded down, so 3.0.
When would you use floor division?
Oh, maybe you need to figure out how many full groups of something you have. Like, how many complete batches of 5 items can you make from 17 items? 17.5 gives you 3. You only care about the whole batches.
Got it. For float division, for floor division.
Yeah.
Okay, what about the true and false values? That's Boolean, right?
Exactly. Boolean data type. It only has 2 possible values, true or false. Notice the capital T and F. and crucially, no quotation marks around them.
And where do they come from?
Often they're the result of comparisons. Like if you ask Python 910, the answer it gives back is the Boolean value false. They're fundamental for making decisions in code.
We'll probably see more of that with conditional statements later.
Definitely.
Okay, so those are the main ones. But the sources also mention tuples, dictionaries, and sets briefly. Can we touch on those? What's a tuple?
Sure. Tuples are quite similar to lists in that they're ordered collections of items. You define them using parentheses instead of square brackets like AD or 1, 2.
So what's the difference from a list then?
The key difference is that tuples are immutable.
Immutable, meaning not changeable, the opposite of lists.
Exactly. Once you create a tuple, you cannot change its contents. You can't add, remove, or modify items.
Why would you want that?
Well, in cybersecurity, for instance, you might want to store data that absolutely shouldn't be altered accidentally, like maybe unique identifiers for approved software in an access control list. Immutability guarantees that integrity. Also, tuples tend to be a bit more memory efficient than lists if you have lots of data that won't change.
Okay, fixed collections. Makes sense. What about dictionaries? They sound useful.
Oh, dictionaries are incredibly useful. They store data not just as a sequence, but as pairs of keys and values. Think of a real dictionary. You look up a word, the key, to find its definition, the value.
Ah, okay. So each piece of data has a unique name or key associated with it.
Precisely. You define them using curly brackets. Inside, you have key-value pairs separated by a colon, and the pairs themselves are separated by commas, like 1 east, 2 west, or username, unzal, status, active.
And the benefit is quick lookup.
Exactly. If you know the key, you can retrieve the associated value very, very quickly, much faster than searching through a long list. Imagine mapping building names to their security zone number. A dictionary is perfect for that kind of predictable storage and retrieval.
Cool. And the last one was sets.
Sets. They're also defined using curly brackets like dictionaries. But they don't store key value pairs. They just store an unordered collection of unique values.
Unique is the key word there. No duplicates allowed.
Correct. If you try to add an item that's already in the set, it simply doesn't get added again. Sets are great when you just need to know the distinct items in the collection, like finding all the unique IP addresses that hit a server from a log file, ignoring repeats.
Okay, that clarifies those extra types. So we have all these types of data. How do we actually hold on to them and use them in a program? Variables, right?
Exactly. Variables are the answer. Think of a variable as a named container, or like a labeled box living in the computer's memory.
And inside the box, you put your data.
Precisely. The label on the box is the variable's name, and the contents are the data value, which has a specific data type, string, integer, list, etc. And the crucial thing is the value inside the box can change, hence the name variable.
So how do you put something in the box? How do you assign a value?
You use the equal sign. It acts as the assignment operator in Python. The variable name goes on the left. The value you want to store goes on the right.
So like my number 810.
Exactly. Or user greeting, hello there. Python is smart enough to figure out the data type automatically based on the value you give it. So in the first case, my number becomes an integer. In the second, user greeting becomes a string.
And if you want to change what's in the box later,
You just assign a new value using the same equal sign. If you later write my number equal 25, the old value 10 is overwritten, and the variable my number now holds 25.
can you make one variable equal to another? Like copy the contents?
Yep. If you have username inzao, and then you write old username, the variable old username gets a copy of the value that username currently holds. So old username would also contain inzao.
Okay. The material had a little code example showing exactly that, changing a username and printing the old and new ones. Helps to see it work.
Now, naming these variables, are there rules?
Yes, definitely rules and also best practices. Rule-wise, variable names can only contain the letters, AZ, numbers 09, and the underscore character.
No spaces, no hyphens.
Correct. No spaces, no hyphens, no other symbols. Also, they can't start with a number. And critically, names are case sensitive.
Meaning username is different from username.
Exactly. Python sees those as two completely separate variables. And another big rule, you cannot use Python's reserved keywords as variable names.
Keywords like if or true or false. Precisely. Words that have a special meaning in the Python language itself. Using them as variable names would confuse the interpreter.
Okay, those are the hard rules. What about making names easy to read? Best practices.
Readability is huge. The standard convention in Python is called snake case. You use underscores to separate words in a multi-word variable name.
Like login attempts instead of login attempts.
Exactly. Or invalidus or count. It makes them much easier to read. Also, try to avoid names that are too similar to each other that can cause confusion.
Keep them distinct.
Right. And while you want names to be concise, they should also be descriptive. Numlogins is way better than just N or X. It tells you what the variable is actually holding.
Makes sense. The material mentioned camel case too, like login attempts, is that used?
It is used in some other languages, and you might see it occasionally in Python, but snake case is definitely the more common and generally preferred style within the Python community. Stick with underscores.
Okay, good tip. So we have data in variables. Now, how do we make programs do different things based on that data? Making decisions, conditional statements.
Exactly. Conditional statements are the core of decision-making in code. They let you execute certain blocks of code only if a specific condition is true.
And these conditions often involve comparing things.
Very often, yes, using comparison operators. Our material lists the common ones. For greater than, for less than, for greater than or equal to, for less than or equal to.
And checking for equality, is it just...
Good question. No, a single equals is for assignment, remember? To check if two things are equal, you use two equal signs.
For comparison. Got it. What about not equal?
That's exclamation point followed by equal sign. And these work for comparing numbers, strings, other types too.
Okay. And the most basic conditional is the if statement. How does that look?
Simple structure. You start with the keyword if, then you put the condition you want to check, like age 18, and then you must end the line with a colon.
The colon is important.
Very. It signals the start of a code block. The lines of code that should run, if that condition is true, must then be indented underneath the if line.
Indentation matters too, then.
Crucial in Python. It's how Python knows which code belongs to the if statement. So if condition, then indented code block.
Okay, if this is true, do the indented stuff. What if it's false? Does nothing happen?
By default, yes.
Yeah.
But you can provide an alternative using an else statement. You write else, also with a colon, on a line after the if block, at the same indentation level as the if, and then you indent the code block that should run only if the original if condition was false.
So if do this, else do that. What if you have like 3 or more possibilities?
That's where elif comes in. It's short for else if.
Okay.
You can have one or more elif statements after the initial if and before the final else, though it's still optional. Each elif has its own condition and its own indented code block.
How does Python process that? If else?
It checks the if condition first. If it's true, it runs that block and skips all the elifs in the else. If the if is false, it moves to the first elif and checks its condition. If that's true, it runs the elif block and skips the rest.
And so on down the line.
Exactly. It keeps checking each elif in order until it finds one that's true, runs its code, and then jumps out of the whole structure. If none of the if or elif conditions are true, then it runs the code under the optional else block, if you have one.
So only one block of code, at most, ever gets executed in an if, elif, else chain.
Precisely. Which is different from having multiple separate if statements.
The material highlighted that distinction. What's the difference again?
If you have several completely separate if statements, one after the other, Python evaluates each one independently. So if multiple conditions happen to be true, the code blocks for all of those true if statements could potentially run.
Whereas with if, elif, else, it stops after the first true one it finds.
Correct. It's a really important difference in controlling the flow of your program.
Okay, got it. Now, sometimes you need to combine conditions, right? Like checking if two things are true at the same time.
Yep, using logical operators. The main ones are and, or, and not.
How does and work?
And requires both conditions on either side of it to be true for the overall result to be true. The example was if status 200 and status 226. The status has to be within that specific range. Both parts must be true.
Okay.
And or.
Or is less strict.
It only required at least one of the conditions on either side to be true for the whole thing to be true. Like if status equals 100 or status equals 102. If the status is 100, it's true. If it's 102, it's true. If it's something else, it's false.
Makes sense. And not just flips the result.
Exactly.
Yeah.
Not negates the Boolean value of whatever follows it. So not true becomes false, and not false becomes true.
The material mentioned using parentheses with not sometimes.
Yeah, that's good practice for clarity, especially if you're negating a more complex condition involving and or. Parentheses help ensure you're negating the part you actually intend to negate and control the order of operations, like if not, status 200 and status 226, the parentheses make it clear you're negating the entire range check.
Okay, super helpful. So conditional statements let us make decisions. What about repeating actions? That's loops, right? Or iterative statements.
Exactly. Iterative statements, or loops, are designed for repetition. They let you run the same block of code multiple times without having to write it out over and over again. Huge time saver and fundamental to programming.
And Python has two main kinds, for and while.
That's right. For loops and while loops.
Let's start with for loops. When do you use those?
For loops are typically used when you want to iterate or loop over a sequence of items. That sequence could be the items in a list, the characters in a string, or a sequence of numbers you generate.
How does the structure look?
It starts with for, then you have a variable name, often called a loop variable, then the keyword in, then the sequence you want to iterate through, and finally a colon-ec.
Like for user in user list.
Perfect example. Underneath that header, you indent the code block you want to repeat. In each iteration of the loop variable, user in your example, will automatically take on the value of the next item in the sequence, user list.
So it goes through each item one by one.
Exactly. The material showed looping through usernames in a list or computer assets. You can even loop directly through a string, and the loop variable will take on each character one at a time.
You mentioned generating sequences of numbers, the range function.
Oh, yes, range. Super useful with for loops if you just need to repeat something a specific number of times.
Yeah.
Range generates a sequence of integers.
How does it work? Range
5 generates numbers starting from 0 up to, but not including 5. So it gives you 0, 1, 2, 3, 4.
Always starts at 0 by default.
Yes, and increments by 1 by default. You can be more specific, though. Range, start, stop, step. Start is the first number inclusive, stop is the number you go up to exclusive, and step is the increment. So range 1, 10, 2, we give you 1, 3, 5, 7, 9.
Okay, for loops are great for iterating over known sequences or a set number of times using range. What about while loops?
While loops are different. They keep repeating a block of code as long as a certain condition remains true.
So it's condition-based, not sequence-based.
Exactly. The structure is while condition, put the colon, followed by the indented code block. Before each potential iteration, Python checks the condition. If it's true, it runs the code block. If it's false, the loop stops and execution continues after the loop.
The key thing seems to be ensuring that condition eventually becomes false, right?
Otherwise, you get an infinite loop. Yes, that's crucial. Something inside the while loop's body usually needs to change in a way that will eventually make the condition false. Often you initialize a variable before the loop starts, check it in the while condition, and then update it inside the loop body.
The examples showed using an integer counter like i5 and updating on inside, or using a Boolean variable like login status that gets set to false when the login succeeds.
Both are very common patterns for controlling while loops. You repeat until some goal is met or some counter reaches a limit.
Now, what if you're inside a loop, either for or while, and you need to exit early, or maybe just skip the rest of the current iteration? That's break and continue.
Precisely. They give you finer control over loop execution, usually used inside an if statement within the loop body.
How does break work?
Break immediately terminates the entire loop it's currently inside. Execution jumps straight to the first line of code after the loop. Done. Finished.
So if you're searching a list and find the item you need, you could use break to stop searching.
Perfect use case. The example showed breaking out of a loop, iterating through assets when it found desktop 20. No need to check the rest.
Okay. And continue. It doesn't stop the whole loop.
Correct. Continue stops the current iteration only. It skips any remaining code within the loop body for this pass and jumps straight to the beginning of the next iteration.
So in a for loop, it would just grab the next item.
Yep. And in a while loop, it would go back and reevaluate the condition immediately.
Yeah.
The example showed using continue to skip processing for desktop 20, but then continuing the loop for any other assets after it.
That distinction is clear now. Break exits completely, continues skips to the next round. And you mentioned infinite loops that never stop. How do you deal with those if they happen accidentally?
Yeah, if your while condition never becomes false or there's some logic error, the loop runs forever. It can freeze your program or notebook. Usually you have to manually interrupt it. The most common way is pressing Control+C in the terminal or notebook interface. Sometimes Control+Z on certain systems.
Good to know the escape hatch. Okay, wow, we have covered a lot of ground.
We really have. The core building blocks.
Yeah, from Python's role, especially in cybersecurity automation, through the different environments like notebooks and IDEs, then diving deep into data types, strings, lists, numbers, booleans, tuples, dictionaries, sets, then variables to store that data, conditional statements, if, elif, else, to make decisions, and finally, iterative statements for a while to repeat actions, plus break and continue for control.
It's a solid foundation. And the source material also mentions having a reference guide and glossary available, which is super helpful.
Right. The guide summarizes concepts like comments, the key functions, print, type, range, and the syntax we discussed. And the glossary defines all those terms from automation to variable.
Absolutely. Getting comfortable with these fundamentals, data types, variables, conditionals, loops, is really the essential first step for anyone wanting to use Python effectively. Especially as we discussed in fields like cybersecurity, where scripting and automation are just so incredibly important now.
Definitely. So as you, the listener, are taking all this in, maybe pause and think, which of these concepts we talked about today, maybe the flexibility of lists, the power of if statements, the efficiency of for loops, which one feels like it could be most immediately useful or interesting for your own work or just your curiosity?
That's a great question. Because understanding these pieces is one thing, but starting to think about how you could combine them, how you could use these building blocks to solve a small problem or automate a simple task you face. Well, that's where the real fun begins.
It really is. It all starts here with these fundamentals.